Hi, my name is Juan Enrique Rubio and I will talk about our article Game Theory-Based Approach for Defense Against APTs. This has been done by myself and my supervisors Cristina Alcaraz and Javier Lopez. We are all from the NICS lab in the University of Malaga. Our main motivation is to address the advanced persistent threats. These are sophisticated attacks perpetrated against critical infrastructures nowadays. They make use of multiple attack vectors as consequence of the integration of modern communication technologies in industrial environments. In this context, the traditional intrusion detection systems are insufficient to successfully detect all the movements of the attacker across the victim network. And just some mechanisms have been proposed to address this issue from a holistic perspective. Among the novel mechanisms, opinion dynamics consists in a collaborative system that enables the traceability of the attack during the entire life cycle that is applicable to multiple industrial sectors. In this paper, we propose a theoretical but realistic scenario to prove the effectiveness of this approach under different types of attack models using game theory. For that goal, we develop a two-player game where an attacker and defender compete for the control of the resources within a modern industrial architecture. Both players have their own movements, rules, and scores associated according to the behavior of the APT in the case of the attacker and the detection system based on opinion dynamics in the case of the defender. This game is executed in different simulations to show the capabilities of this algorithm in order to suggest the optimal configuration for the integration with other defense solutions. Before presenting the game itself, let's take a look at the detection approach based on opinion dynamics that we aim to validate here. Let's present the general idea. The opinion dynamics is a distributed consensus algorithm to exchange information between agents in a network. Every agent has its own opinion about something that is exchanged with its neighbors in order to reach a consensus, like individuals in a society. In our case, the opinions will represent the level of anomaly reported by each agent, so that in the end, the network is fragmented in groups of opinions that represent attacks with different level of severity. To give you some background, this is an algorithm that we proposed in the past, demonstrating its traceability features and its applicability to multiple industrial scenarios. In the real world, the set of agents capture information from individual devices in the industrial network before running the opinion dynamics correlation. This information comprises different parameters about communications with other nodes or the consumption of resources like memory or CPU, for example. This approach is even flexible to integrate external detection systems with the agents to calculate their opinion value. In the end, these opinions provide information about the security state of the network in real time. Here, we leverage game theory to assess the accuracy of this mechanism when deploying response techniques that use the information provided by the opinion dynamics algorithm. For this goal, we create an attacker and defender model to study the optimal configuration of different response procedures to eradicate an APT. In the context of industrial networks defense, game theory permits to analyze hundreds of scenarios, improving decision-making when dealing with many levels of criticality, different network sizes, interconnectivity, or security policies. At the same time, it also helps to validate the effectiveness of the opinion dynamics with different strategies, and for this we have created TITO. It represents a two-player game with attacker and defender with imperfect and incomplete information because no one of them knows the location of the adversary within the network or his score. According to a second level of classification, this game can be considered as dynamic and stochastic, as both players take their actions based on the state of the network and they are exposed to events that affect them in a probabilistic way. This contrasts with most of the game theory approaches of this kind that are commonly based on static games with perfect and complete information that find an optimal strategy when a steady state of the game is reached, usually the Nash equilibrium. In turn, a real control system faces a dynamic interaction game with incomplete and imperfect information about the attacker, as we do in our game. In TITO, both attacker and defender fight for the control of the infrastructure, which plays the role of the game board. It is designed in a realistic way with a graph G that contains nodes and links to connect them, So we represent a network that is composed of two sections connected by intermediate firewalls. On the one hand, an IT section with corporate devices where all of them are connected with each other, and then an OT section that includes traditional industrial assets like SCADA servers, controllers, or field devices. In our simulations, both sections are generated using random distributions that model the architecture of real industrial systems. It is also necessary to define some concepts that will be useful to understand the game dynamics. We define the criticality of a resource as the risk subject to that type of device within the organization, which is used by the defender to assess which nodes should be recovered to minimize the impact of the APT. For example, the criticality of a sensor is low compared to the SCADA system, and resources in the OT section are more critical than the IT devices. For this, we create an ordered set of criticality values based on the type of node. Besides the criticality, the vulnerability of a node tells how easy it is for the attacker to compromise that node. In this case, we will assume that this value is opposed to the criticality, in the sense that field devices will have lower protection, while high-level systems that control the industrial process will have advanced security services. In order for the OT section to be resilient against denial of service attacks on their links, we also consider that that section presents channel redundancy to ensure that the detection algorithm exchanges the opinion among agents even when some links are down. This way, all nodes in the OT section have an additional channel to connect them with another node, but these redundant edges are only used to transfer the anomaly values between agents. We now describe the game dynamics. There are two players, the attacker and defender. For simplicity, they are represented with A and D, and as we have mentioned, both of them compete for the control of the game board. In our approach, the game begins at t0 and continues as t approaches infinity. Every time in the game, the attacker and the defender has a turn to play. The attacker is the leader and the defender moves depending on the resulting state of the board. The state of a node is equals to 1 if it is compromised at time t and 0 otherwise. We assume that the state of all nodes is 0 at the beginning of the game. A movement is performed by the attacker or defender to change the state of a node at a time t according to their respective attack and defense models. Basically, the attacker can take over healthy nodes of the network and the defender can recover a compromised node to return its state back to 0. Every movement performed by A or D generates a reward depending on the ultimate goal of the player, which determines the score. In this case, the attacker receives 1 point when a new node is compromised, and the defender obtains the same reward when he recovers a node that was compromised. Besides a reward, every movement also implies a cost for the player. This represents the fact that the attacker can exploit vulnerabilities that in turn may cause its detection, while the defender may need to stop the production change to recover a critical resource. The utility is the total number of points scored by a player at a given point in time. It is calculated as the reward minus the cost of the movement. The overall goal for both players is to maximize this value until the game is over. To summarize, the attacker earns points as it spreads the threat across the infrastructure, while the defender increases the score when those infected nodes are recovered. The utility value just gives an idea of the number of points scored to evaluate the strategy of the players. This strategy is different for each player. The attacker looks for vulnerable nodes in the network while avoiding its detection, while the defender follows an adapted strategy based on the last movement of the attacker. Also, there is a termination condition to determine who wins a game. As for the attacker, the game is over when he manages to complete all the phases of the APT. And for the defender, the victory is achieved when all nodes infected return to the original state. For the interest of the analysis, we define an additional third termination condition, the draw. This happens when the attacker completes its strategy, but the defender also performs a last movement that recovers all nodes. Even though this may be considered as an attacker victory, the defender still finds the trace to the threat in the end, which shows the accuracy of the detection technique going after the infection. With this, the dynamics of the game and the basic rules have been presented. However, we have to specify the movements of each player, beginning with the attacker. In our previous works, we formalized the APT as a sequence of stages that model the behavior of these attacks. More specifically, the attacker begins by recognizing the victim network and then he performs the first intrusion. From that moment, he starts discovering potential nodes to propagate the infection. For the election of the node to take over, we assume that the attacker scans the network to find the most vulnerable devices, using the function defined before. Once the attacker has perpetrated this lateral movement, he can block the communication channel to decoy the defender by avoiding the opinion exchange between agents. Finally, he causes disruption to the infrastructure or exfiltrates sensitive information. These attack stages correspond to different movements performed by the attacker. Each of these movements result in a different cost and reward. As for the reward, to hold asymmetry between both players, they will receive 1 point every time they gain control of a node that previously belonged to the adversary. And for simplicity, we consider that all stages in the attacker have the same reward. With respect to the cost, we have to recall the opinion dynamics algorithm in relationship with the defender goals. We assume all the network resources are monitored by anomaly detection mechanisms, so that these stages have a different effect on the anomaly value reported by every agent, which is represented with its opinion, as we have presented before. Therefore, the cost will depend on the severity of the security alerts that are generated, because they increase the probability for the attacker of being detected. This is modeled in our simulations in a probabilistic way, with an ordered set of detection probabilities that are associated with each attack stage. As for the strategy applied for the attacker in TITO, it will depend on the state of surrounding nodes that are vulnerable at every time of the game. This strategy continues until one termination condition is reached, as long as the attacker poses at least one node. The precise behavior to define the chain of attack stages is the following. The attacker always starts with an initial intrusion, which is a randomly chosen node from the IT or OT section. Then, the attacker tries to make a lateral movement to compromise a firewall in order to penetrate the other section of the network. Once the attacker penetrates the other section, we assume he must complete a minimum succession of 3 lateral movements before finally executing the destruction of the resource. In that case, the game terminates complying with a victory of the attacker or a draw, depending on the movements of D. In this case, the defender can prevent the completion of this chain if he detects the attacker and successfully eradicates the infection from all nodes. In order for the attacker to avoid that situation, a link removal can be executed. In TITO, the attacker makes this movement when the defender manages to recover 3 nodes in a row, which represents the situation where D is close behind the attacker on the board, as explained in the following. We now focus on the defender model to explain how the recovery of nodes works using the information provided by the opinion dynamics algorithm. As discussed before, the ultimate goal of this paper is the analysis of the opinion dynamics technique to detect APTs. The defender aims to locate the attacker position across the whole network, keeping track of the anomalies reported. For this, the defender executes that algorithm at every turn of the game to check the state of the network, and optionally perform a node reparation. More specifically, he firstly selects the most affected node according to the opinion of the agent that is monitoring it. Then, the defender decides whether to heal that node or stay idle in that turn, depending on a threshold. In other words, if the opinion given by the agent surpasses that threshold, the defender recovers it. This movement has a reward of 1 if the node repaired was actually compromised, otherwise is 0. Regarding the cost, it is equivalent to the criticality of the node that is recovered, because critical resources are subject to a potential stop in the production chain and usually need a greater effort to repair them. This process continues until all compromised nodes are repaired or the attacker completes the set of stages. The reparation procedure is the main movement of the defender, However, the defender adopts a dynamic behavior that can include three additional configurations. On the one hand, by local opinion dynamics, we mean executing the correlation approach with a subset of nodes of the original network, as a global correlation in a synchronous way may not be feasible for all the nodes in a real environment. This subgraph is built with the candidate node on all its child node in a G graph located at a distance of one or two hops. Secondly, we use the redundant links that we described before when the attacker destroys a link, so that opinions will be transmitted using those links only in that case. Lastly, we consider the inclusion of honeypots in the infrastructure that are vulnerable nodes that are chosen randomly. These are used as a bait for the attacker, so that if he tries to compromise them, a higher anomaly will be generated that will reveal his position, helping the defender. In our tests, 5% of the total number of nodes have been considered as honeypots, which is a minimal value to show the effectiveness of this response technique. Once the attacker and defender have been described, we now show the results of some experiments with the game. As we have discussed already, the objective is to find the best strategy for the defender given an APT perpetrated by the attacker. We have compared the percentage of victories of each player across multiple games. More specifically, we have run 4 test cases with incremental configurations for the strategy of the defender. A local opinion dynamics detection around 1 hop of distance from the observed node, local detection with 2 hops of distance, the addition of redundant edges in the network, and the integration of honeypots within the topology. For all of these test cases, we execute 10 sets of 100 games, and we run them with 3 network sizes of 100, 200, and 500 nodes. After running the experiments, we show the box plots that represent the average of the percentage of victories for the 3 network configurations. In the first test case, the attacker experiences a higher rate of victories because he easily escapes from the defender detection, which only leverages 1 hop of distance from the affected node. Therefore, the best case scenario for the defender happens when he only manages to follow the infection until it is eradicated in the last turn, resulting in a draw. Let's take a look about test case 2. With the introduction of more nodes covered by the local opinion dynamics, the percentage of victories for the defender increases significantly, which shows the importance of applying a wide area of detection. However, the number of attack victories and draws still remain moderate, since the defender has not sufficient accuracy as to keep track of the attacker when the removal of links is performed and the detection is avoided. The implementation of more defensive protections results in a higher number of victories for the defender in the third test case. Here, the redundancy makes the defender able to trace most of the attacker movements, including when the attacker wants to get rid of the detection, which is more evident in smaller networks. And yet, the defender must successfully recover all the compromised nodes across the network that may continue the attack and be far away from the current detection focus, which still causes a low number of attack victories and draws. Lastly, the addition of honeypots are a secure way for the defender to ensure the highest number of victories. The presence of these devices triggers severe anomalies when the attacker tries to compromise them. They are detected by the defender to rapidly locate the current affected node, as long as a wide area of detection is used. We can also analyze the overall score in these test cases. Here we show the average score for both players. We see how the defender obtains a higher score in all cases and a slightly higher score when using low-size networks, since he experiences greater accuracy in the reparation of nodes. Also, the score decreases for both players as test cases implement additional defense measures. This is because on the one hand the attacker generates more anomalies and therefore more costs due to the link removal attacks to avoid the detection. On the other hand, the defender has more candidates to recover due to the increased number of anomalies, and does not always have a high accuracy in choosing them. To conclude, by means of game theory, we have demonstrated that opinion dynamics is valid for catching the compromised nodes of the attacker when it is applied with a minimally wide detection area of at least 2 hops of distance from the observed node, and it is coupled with effective response techniques like the honeypots or redundant links. Of course, there is still a lot of work to be done, which includes the reproduction of these test cases on a real environment, as well as the design of a multiplayer game that comprises more than one thread taking place at the same time. Thank you for your attention, and I'm happy to answer your questions.